Okay, so have you ever noticed how many products are claiming to be pure these days?
Yeah,
It's everywhere, right?
it's on every label.
Yeah. But our deep dive today is going to make you rethink what pure even means.
Yeah, it's true
Right.
what you're saying. Our everyday language, it doesn't always match up perfectly with how scientists define things, and I think that's where some of these misconceptions come up.
Exactly, and that's where our source material comes in. Is matter around us pure?
Hmm.
Sounds kind of basic maybe, but trust me, this is going to change how you see everything around you. Ready to dive in?
I'm ready. Let's do it.
All right, so let's break it down. In the science world, a pure substance, what does that even mean?
So a pure substance, it means it's made up of only one type of particle.
Okay, so kind of like if you have a basket of apples and it's all apples, nothing else in there.
Exactly, yeah. All apples, nothing but apples.
Okay, now imagine you take that apple basket and you start throwing in some oranges, maybe a pear for good measure. What do you have now?
Then you've got yourself a mixture. You've got a combination of two or more of these pure substances. And the key is each one keeps its own properties, right? So the apple's still an apple, the orange is still an orange, even though they're mixed together.
Which brings us back to that pure milk carton we were talking about.
Yeah, the milk carton, that's a really good example because milk, it looks totally smooth and consistent.
Oh, yeah. You think it's pure.
Right, but it's actually a mixture. It's got water, fats, proteins, even sugar, lactose, all hanging out together in that delicious blend.
So it's like finding out that, I don't know, your favorite band isn't actually three people, but there's a whole orchestra hiding behind the scenes making those catchy tunes. So if milk is this mixture pretending to be pure, what other kinds of surprises are hiding in this world of mixtures?
Well, we've got a whole bunch of different kinds of mixtures, right? But in general, we can think of them as either homogeneous or heterogeneous. A homogeneous mixture, that's like salt water. It's got a really uniform composition. So it doesn't matter if you take a sip from the top or you scoop some from the bottom, that ratio of salt to water, it's going to stay the same.
Okay, so it all blends together perfectly. Like you wouldn't even know it was a mixture just by looking at it.
Exactly. But then you've got heterogeneous mixtures.
Yeah.
And those are much easier to spot. Think of a salad, right? You can see all the individual parts. You've got your lettuce, your tomatoes, your cucumbers, all separate.
They're all kind of doing their own thing, even though they're in the same bowl, right?
Yeah, exactly. And that's actually what this copper sulfate and potassium permanganate activity in the source material is showing. Some of those mixtures, they look totally uniform, like a homogeneous mixture. But others, they've got those separate layers or those visible particles, so you know right away, okay, this is a heterogeneous mixture.
It's like a science experiment, but you can actually see it happening.
Okay, so speaking of seeing, what happens when we zoom in even closer on these mixtures, particularly the homogeneous ones?
That's when we get to solutions. Solutions are pretty fascinating. Think about dissolving sugar in water. The sugar, it looks like it vanishes, right?
Yeah.
But it's still there. It's just spread out evenly throughout the water. And that's what we call a solution, a special type of homogeneous mixture.
So it's not just solids dissolving in liquids then?
Not at all. Solutions can be all kinds of things. Like, did you know even the air we breathe? That's a solution. It's a mixture of different gases, mostly nitrogen and oxygen, but they're all perfectly blended together.
Wow. I never thought of air that way. Okay, so in a solution, we have a solute, which is like the thing that's being dissolved, and the solvent, which is doing the dissolving.
Exactly. And then there's another important concept here, concentration. That's how much of the solute is dissolved in a certain amount of solvent, which is important because, the concentration of medicine, that's what determines if it's going to work or not, right?
Yeah.
It can be the difference between a medicine helping you and maybe not helping you so much.
Exactly. It's all about finding that right balance,
Yeah.
right? But, sometimes things don't dissolve perfectly. Sometimes they've got other ideas.
Okay, so what happens then? What are we talking about now?
We're talking about suspensions. Think back to that experiment with copper sulfate, potassium permanganate in the source material, the one where some groups ended up with mixtures where you could see the separate parts. Those are suspensions.
Oh, right. It's like they just wanted to stand out, be their own thing. So instead of dissolving, the particles in a suspension are just kind of floating around.
Pretty much. They're bigger than those in a solution, those particles. And because they're bigger, they do this cool thing where they scatter light. Like, you ever notice how you can see a beam of sunlight when it shines through a dusty room?
Oh, totally. Or like when a flashlight cuts through fog, it's way more visible.
Exactly. That's that light scattering. The dust or the fog, those particles are big enough to bounce the light around so you can see it. Now, suspensions, They're a little more, I don't know, unpredictable than solutions. Leave them alone for a bit and
Everything settles down.
exactly. You get that separation like if you have a glass of water with sand in it and you forget about it.
Oh, yeah. You get that layer of sand at the bottom.
Exactly. And remember the source material talking about filtration. That's how you can separate a suspension. You're basically just straining out the bigger particles.
So kind of like when you make coffee.
Exactly.
Hmm.
Filtering out those coffee grounds. Now, this is where it gets even more interesting. Because there's another type of mixture we haven't talked about yet. And it's kind of like a bridge between solutions and suspensions. Colloids.
Ooh, colloids. Okay, so these are like the in-betweeners of the mixture world.
Yeah, you could say that. Remember how we talked about milk? It
Mm.
looks all smooth and homogeneous.
Total innocent. Yeah.
Right. Well, get this. Milk is actually a colloid.
Yeah.
The particles in it are bigger than solution particles, but smaller than suspension particles. So they're kind of in this in-between zone. Too small to see, but still big enough to scatter some light.
Is that why milk kind of glows when you shine a light through it?
Exactly. That's the Tyndall effect. Same thing that makes beams of light so visible in a forest.
Yeah.
It's really pretty, actually.
Wow, I never knew that. So that, like, magical forest light is just water droplets in the air.
Pretty cool, huh? So how do we know if something is a colloid or just a really, really fine suspension?
Good question, right? Well, it comes down to stability. Remember, suspensions like to settle.
Right.
Colloids, they don't do that. They stay mixed even if you leave them alone.
No drama with colloids.
Exactly. And you can't just filter them out like suspensions either. They're a little more stubborn. Okay, so we've talked about mixtures, but now let's get down to the nitty-gritty, the absolute basics of what makes up everything around us.
We're going even deeper.
Okay, I'm ready.
We're going subatomic. We're talking about elements and compounds.
Okay, so this is like breaking down the universe into its tiniest Legos.
Perfect analogy. Elements, those are the simplest pure substances. They can't be broken down any further. Each one has its own personality, its own set of properties. Think oxygen, gold, hydrogen, all those superstars on the periodic table.
The ingredients for, well, everything.
And when you combine two or more of these elements together, you get something completely new, a compound.
So it's not like mixing the copper sulfate and potassium permanganate. It's different.
Very different. See, compounds are formed through chemical reactions. That means the atoms of the elements, they decide to share electrons and form this, like, super strong bond. A good example from your source material is iron and sulfur.
Oh, yeah. That's where things got heated up, literally.
Literally. See, when you just mix iron and sulfur together, it's just a physical change. There's still iron and sulfur, but add a little heat.
And it's a whole new ballgame.
Exactly. Heat provides the energy for a chemical reaction, and bam, you get iron sulfide. And iron sulfide, it's got a totally different personality than iron or sulfur on their own.
So it's like mixing flour, sugar, and eggs on their own. Fine. But add some heat and...
You've got a cake. Something totally new and different. But how do we know if something's just a physical change or if it's a full-blown chemical transformation? That's the question.
Yeah, it's like, how do we tell if we're just rearranging the furniture or if we've, like, renovated the whole house?
That's a great way to put it. With a physical change, you're just changing how something looks, maybe its state, like solid, liquid, gas. But the chemical makeup, that stays the same.
So, like, water is still water, whether it's ice or steam.
Exactly. But a chemical change, that's when you're creating something totally new with its own unique properties.
So, like, burning wood, you can't get the wood back after that.
Perfect example. You start with wood, and you end up with ash, carbon dioxide, water vapor. They're totally different. And you know what? The source material actually gives us a really cool example of this. A burning candle.
Oh, right. What's so special about a burning candle?
Well, it's kind of doing both, right? You've got a physical change happening when the wax melts. It's still wax, just in a different form. But then you've got a chemical change happening when the wick burns and the wax vaporizes. You're creating new substances and releasing energy as heat and light.
Wow, it's like a little chemistry show right there on your table.
I know, right? It's pretty amazing.
It really is. So we've gone deep on mixtures, dug into solutions, and explored the core components of, well, everything. Elements and compounds. But how does all this knowledge actually apply to our lives?
That's the exciting part. When you understand these concepts, it's like you're seeing the world with new eyes. Suddenly you're noticing mixtures and solutions everywhere. Your morning coffee, the medications you take, even the air you breathe, it's all connected.
So, like, when I'm making my coffee, I'm basically a chemist.
Exactly. You're using hot water, the solvent, to extract those delicious compounds from the coffee grounds, the solute. And the longer you brew it, the higher the concentration of those compounds and the stronger your coffee will be.
Mind blown. And what about those sneaky colloids we were talking about before? The ones that seem so pure but aren't?
Ah, yes, the masters of disguise. Colloids, they're everywhere, and they make our food so much more enjoyable. The smooth texture of yogurt, the fun wobbliness of jelly, the airy lightness of whipped cream, that's all thanks to colloids.
Those tiny particles really do make a big difference.
They really do. And it's not just food, right? Understanding mixtures, solutions, pure substances, it helps us make better choices in all aspects of our lives.
So whether we're trying to pick the right cleaning products, understand what's in our food, or just appreciate how complex and amazing the world is, it all comes back to these basic principles.
I completely agree. This stuff, it's not just for scientists and labs, it's for everyone.
It really is. So, to our listeners, what was your biggest takeaway from today's deep dive? Did you have an aha moment? Did something surprise you? Let us know. Keep those questions coming because curiosity is what fuels discovery. Until next time, keep exploring and stay curious.